All right, so thanks everybody for coming. I'm pretty excited to be here in front of you all. I wasn't here last year, so for me it's almost like seeing it quadrupling in size, which is pretty exciting. So today I'm going to be talking about connecting LabVIEW to everything else, and in particular we're going to be talking about APIs. So I put kind of a funny little cartoon up there about how, I don't know, who around the office uses the word API all the time. Yeah. So before we jump in, so basically we're going to be exploring how to provide connectivity into the LabVIEW applications that you're writing from the outside world. How to allow customers and users of systems that you're building to connect in. And so as you all know, we're living in this mobile era, as Rob was talking about, and everything is connected. For our systems to really be part of that world and for our products and our customers' products to be successful, they really need to be able to be connected to and to connect. So hopefully I'll be sharing maybe some new ideas or new perspectives on ideas, but you guys are the experts here. And so I'm really excited to hear some feedback from you guys about how what I'm talking about applies to the systems you're building so that I can learn as well. So again, let's keep it a dialogue and let's talk about building systems with LabVIEW. So when you make a connection, you create an interface, which is basically a point of interaction between components. These components can be hardware, they can be software, they can be combinations of hardware and software. Components can have subcomponents. When you're calling a subcomponent, you're calling through interfaces. These components can be local, they can be remote. Everything happens through interfaces. And the point is, if you're a programmer, you are an API designer. So pop quiz, who knows what API stands for? Fabioli. Very good. So maybe that should be a CLA exam question, since APIs are so important. No, it doesn't stand for the Advanced Protocol for Instruments. After my presentation, maybe that'll be confusing both because I mentioned it and what I'm going to talk about. Hopefully not. I'm sure you'll all get it right, but we know the CLA, they love trick questions, right? And trick questions. So I think a main point here, too, is professional software developers are expected to be able to call into APIs of other systems, and they're expected to create them for their system. So, you know, you guys are building a system, and your customer's software department says, oh, yeah, well, you know, your system should just call into the API that we created into our database, and it's using, you know, a JSON-based, you know, web service. You guys can do that, right? Or, you know, your system, you know, we need to get the health of the system. So can you just provide us with an API that we can call from Java? You know, we can do XML-based REST APIs. So you guys can do that, right? And I think if we're going to be able to quickly adapt to our customers' needs and to integrate with their systems, it's expected of us to be able to create APIs. So there's different aspects of API design. You know, APIs are kind of everything. There's, you know, the design of calls and behaviors, whether these are, you know, by value or by reference. Calling sub-VIs is calling through an API. When you're building a class, that's an API. Whether they're local or remote, have connectivity types of questions, whether the connection's always there, what are the latencies, whether it's, you know, deterministic messaging or just kind of broadcast. There's technology aspects. Is it over HTTP? Is it using XML or JSON? There's security considerations, of course, and versioning. I'm not going to get into too many of the different branches of these different aspects of APIs because, I mean, we'd be having a 2-day summit on API development. In fact, I encourage everybody to Google, you know, API design best practices. The internet world, web apps, software as a service, they're all about APIs, and they've got some really good advice for creating APIs to commercial products. A lot of these APIs have thousands of users. The number of users of APIs to our systems will probably be much fewer. But we'll dive in and talk about some stuff hopefully is relevant to you all. Okay, so I'm really going to be talking about building APIs to your systems for your customers. Again, I hope it's relevant to you all. Really, you know, APIs are so prevalent today. our office admin staff knows the word API. They don't know what it means, but they know that everything should have an API. They hear software developers joking, man, I wish the espresso machine had an API so I could make coffee from my desk, right? So I could build an app to do this with that. But in general, it's a term for a mechanism that allows other software applications to make calls into a system, send messages, call a function, get some data. So it's really what makes a system useful in the connected world, and it allows us to connect to it. So this diagram here kind of shows, the way that we kind of see the world today. You have a system, and it's able to connect between other computers, mobile laptops, touch devices like tablets and cell phones. And also it's calling into services, and services are calling into it where we don't know where they live. And it kind of doesn't matter where they live because they're just out there. So in order to be part of this, we need to do APIs. And this is coming, fast. We're kind of behind, I think, in terms of where we are with respect to some of this technology. Rob was mentioning our users expect this. They're used to getting apps that get updates, that push data into the cloud. And when we're building systems, there's a lot of features that they expect. They don't want to deal with this complexity, artificial complexity, that oftentimes we're presenting to them. Okay, so I wanted to kind of shift a little bit and talk about what's the real business value of providing APIs besides the fact that everybody's talking about them and they're cool, web, internet type stuff. So first of all, the reason why APIs have business value is they allow the products to be more than what's in the box. So if somebody's developing a product and it sits on a lab bench or in a lab somewhere, basically the company selling that product can also sell web-based interfaces, iPhone apps, and if it's connected, they can provide great updates and services to the customers. They can perhaps with the user's consent monitor their usage, provide good improvements to the product, maybe push ads to them based on how they're using it. It allows customers to solve more business problems. So customers, they've got real business needs to do things that maybe out of the box your software doesn't do. If they have an API to your software, they can automate tedious tasks. Maybe they can add features through extension points, and they can integrate it into other business systems. So let's say their IT department or their process people need to monitor what's going on in a system that you've built. They can call into the APIs, get health information, query the logs, write it to a database, do statistical process control. Maybe they're feeding recipes down into it and getting results. It also creates customer loyalty and lock-in. And so this adds value to the vendor of the product. And basically what ends up happening, if a product has an API and people are doing development against that API, two things kind of happen. One is they have to learn the API. So there's an investment of time and emotions into understanding how to speak the language of that product. And then there's the actual work product that goes into calling the API. There's the software in their systems that they've developed that glues your system in with their system or other systems, and that investment and that inertia really causes the end customer to become a lot more dependent upon and married to the product and more likely to provide feedback to the vendor of the product. Your APIs become somebody's skill set. It might show up on their job resume. Something, oh yeah, I know this API, I can talk to this instrument. When they go and they leave their current work, they might say, oh, well, I recommend that we use this instrument or system or technology because I already know how to talk to it. I've already got a library in LabVIEW that I can use to talk to it. So it really does make sense. It's not just about the fact that APIs are cool. So kind of tying back to systems, the point being APIs are important for systems in a connected world. So at JKI, we often help our customers build lab instruments. Sometimes it's semiconductor equipment, big instruments. Sometimes it's one-off systems like Matt was showing, the gear tester. But it basically needs to behave like a product. And I'm going to be showing you guys stuff from the perspective of like a small touchscreen lab instrument to kind of drive home some concrete examples of how APIs add value and kind of showing some of our implementations. And I'll get into both a demo and show a little bit of LabVIEW code too. So again, I hope you guys find this relevant. When you see this benchtop instrument, I hope you think about your own system and how these concepts apply to you and your customers. So the idea of instruments having APIs so they can be integrated into other systems really goes all the way back to like, what, 1976 when NI was founded, building GPIB hardware to allow computers to talk to boxed instruments. I was born in 1976, so I might not get all this right, but basically it was a long time ago. And basically over this GPIB bus, these instruments, at some point somebody standardized a protocol for sending commands down to instruments, which is called SCPI. How many people in the room know SCPI or have heard of it? How many people have really never heard of or used it, or maybe just haven't used it? Yeah, it's kind of interesting. A lot of the new LabVIEW CLAs that I see, never used it, and that's kind of crazy for me. Kind of shows my age. I've been doing LabVIEW since I had hair. But it, yeah, there you go. And the idea is over this. I'm using my laser pointer to point to my screen, so I can. You guys don't see that? A lot of things happen when you get older, huh? So over this GPIB cable, the computer using maybe a text-based basic environment, HP basic, whatever that is, would send commands down here like measure the voltage, and then the instrument would say, okay, the voltage is 1.2 volts, or you could measure the current, and that API to the instrument is what made that instrument valuable in the context of a larger system. Maybe it's a rack of these instruments with some software that integrates them all into a test system that has subsystems, which are boxed instruments. And it allows the automation of the testing so that you don't have a manual tester coming up there pushing buttons, rewiring things, pushing more buttons. Again, this goes way, 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 way back. Just to prove how far back it goes and how important it is to all of us here in this room, try calling IEEE 488 and see who picks up the phone. How many people actually knew that phone number? Okay, so now everybody does. I think so, but I don't know, it's just so nice. I just remember what it is. It's one of those few numbers I know because I've got everybody on speed dial now. So the point is, instruments are systems, and they have APIs. It's what truly makes them useful as components of larger systems, and it really adds tremendous business value to users. All right, so the next step in this evolutionary process was the creation of LabVIEW to allow you to create virtual instrumentation. The software is the instrument. The next thing that happened is now, and then in LabVIEW, we could call the NI modular hardware so that users could create software-defined rather than vendor-defined instruments. And that was really, a major focus of last NI week with the vector signal transceiver, that you could write your LabVIEW code and it's defining the behavior of your instrument. The software is the instrument. Well, once you define the behavior of your instrument, then you need to also provide APIs to that instrument so that it's then useful, integrated into a larger system. If you guys are curious, I wrote a blog article about, I forget the exact title, but what happened to virtual instrumentation. I think it maybe is a disservice that VI front panels are called virtual instruments because they only really do a subset of what instruments do. Instruments have state, they have APIs that you can communicate, and if they conform to a standard interface, you can swap out one instrument and plug in another. And when I see frameworks with active objects that have interfaces that you know, have like maybe inheritance and things like that. I think, wow, that to me that sounds like virtual instrumentation. So as time goes by, the size of hardware we can run LabVIEW on continues to get smaller and smaller, and the opportunities for people in this room, the customers of people in this room, to ship LabVIEW on higher volume, lower cost commercial products continues to grow and grow, and I think that that's just really great for us because it means really that, you know, vision of LabVIEW everywhere is becoming closer and closer to a reality. So just kind of quickly here, the guy on the right there is a little stealth PC. It's a little fanless PC. It's like $1,000, runs Windows 7. You can plug in your NI compact DACs and your NIC Rios into it and stuff like that. And we've had a lot of luck using that for prototyping, and I'll show you guys an example of something we've created using that. And I'll talk about some of the business value as well. So back to APIs and instruments. So I'm going to show you guys a demo here of basically my laptop communicating to a benchtop instrument that's powered by LabVIEW and that has a touch screen. And the purpose of this demo, in addition to showing you cool LabVIEW controlled touchscreen demo stuff in a box, is really to show the value of APIs. So I want you guys to think about that. When I show you these cool things, realize, wow, it's APIs that are allowing that to happen. So what I'm going to go ahead and do really quickly, and again, this is a live demo, so things are inevitably going to go wrong, so just set your expectations right now. Okay. Last time I couldn't get this picture-in-picture window to go away. So this is a touchscreen instrument, and basically I'm going to try to both show you and do it at the same time. So if I hit start, I can run a process, and the process runs, and we get a progress bar, and we get thumbs up. Process worked. And then I'm going to complete the process, and there it is, finished. So I was pushing the buttons here, but what would really make this useful is if it had an API. And let me see if I can. There we go. I'll move it out of the way so that then I can, maybe I should quit it and start it up again. Nope. It's happy where it is. So let me check my network. I'm going to connect to the JKI instrument demo. And so just as a disclaimer, I've got a Wi-Fi router. And actually, this is a good explanation of what I'm going to show you. So I've got a Wi-Fi router, and this thing is basically configured to connect to the Wi-Fi. And my laptop is also connected to the JKI instrument demo Wi-Fi. And I am going to attempt, let's see here. Oh, that actually worked, okay. So I'm going to telnet, which is basically just opening a raw TCP/IP connection to my instrument, which is its name on the network, on a specific TCP/IP port that it is listening. And it sent me back some jargon here, which means I've connected. And what I'm going to go ahead and do is type recipe status, and it says that it completed the last recipe that I ran. So that's giving me an indication that it's currently in a state where it can run a recipe. And so I'll do recipe run, and then you'll have to take my word here. Yeah, so if only I had 3 or 4 hands here. So I'm going to zoom out and then zoom on. Too bad I can't pan too. No, I'm gonna wing it here. I've got like four controllers in the room. If we had a fifth, I'm gonna be in trouble. So I'm gonna hit run, and it's running my instrument. And so basically, it's doing SCPI over TCP/IP wirelessly to the instrument. Yeah, it's pretty cool.
And so like you're telnetting to this right now, but you could get this from any device that has the ability to send TCP.
Yeah, so what would be really cool, let's see if I can actually do it, is if you could write a LabVIEW VI that used Visa to open a connection and write a Visa command, recipe run, and then wait and get some data back. And let's see if I can make this happen too without.
So this is going to run on VM on your computer.
Right. So this virtual machine is basically just my parallel. So it's running on my Mac. Nothing fancier than the fancy stuff I showed you. So here, let's get it queued up to run a recipe. And then I'll run this. Okay, hold on. Network, bridged Wi-Fi. There's no error handling on here, so let's. The connection for a given session has been lost. Well, let's try this. Let's open.
Yeah, maybe the telnet is still
Oh.
on.
All right. So it ran, and you can see that. I don't know why there's still an error, but anyways, it said OK recipe run. That means it got the command OK, and I can do something here, and let's say recipe stat question mark. It says it's still running. I hit the final done button, and now it says that it's complete. Cool. So basically what you're seeing now is the programmer can write code that's running on a different computer. Maybe it's a test system that integrates this biotech instrument. Maybe it's a developer writing some code where the robotic pipetting machine is filling a 96-well tray, and then another robot comes, picks it up, sticks it into the sample tray of the biotech instrument, and then tells it to go ahead and start the run. So now they can use my biotech instrument in an automated lab setting. So that certainly adds a lot of value to the people who are buying this benchtop instrument, or JKI's customers. Okay. And that's not the last demo either, so hang tight. There's still a lot of opportunities for things to go horribly wrong. All right. So basically what I'm going to do really quickly is show you guys a little bit in bullet form the architecture of how this API was implemented, and then I'll actually show you the LabVIEW code that handles this command, so that maybe it'll resonate a little bit with you about how you could implement it, or how it relates to how you've implemented something like this in the past. Like everybody, JKI has a framework that loads our system up, all of its components, right, all of the agents, and starts them up and gets them happy. And if the system provides a SCPI interface, it basically launches a TCP/IP server that listens on the TCP/IP port. And when a TCP/IP client makes a connection it spawns a connection handler for that TCP/IP connection. And that's going to be listening for SCPI commands. When it receives a complete command, what it will then do is it looks at kind of the header of the command, the part that said recipe or res, and it says, okay, which of my subsystems is responsible for handling recipe commands? And it says, oh, I'm going to pass it to the recipe engine, and it's going to pass it the run command or the status query or the progress query, and then there's a VI inside of that agent or subsystem or component that is going to handle the progress query, the status query, and the run commands. So as promised, let's see if I can give you guys a quick little demo here. So this part is going to be potentially confusing, because what I'm going to do is I'm going to go into Parallels, which is running on my Mac, and I'm going to open a remote desktop connection into the magic box. So this instrument, benchtop biotech instrument, is running Windows 7. And it's basically just a little, PC. And for early prototypes, what we find at JKI is that doing the early prototypes in Windows makes the development process very, very rapid. In fact, and so what you're seeing here is basically just a user interface showing all the different system components that have been loaded up. And we're running the LabVIEW development environment inside of this production instrument, which allows us to very quickly debug. Once we're ready to deploy, we can, of course, harden things down, build executables, version them. Instead of Windows 7 Professional, we can run Windows 7 Embedded or apply the registry hacks like Matt was talking about, different things that make it a little bit more hardened, basically. So again, the screen that you're seeing is actually the PC that's running inside of the Windows machine. And this is fantastic for debugging. So what I'm going to do is I'm just going to open the folder in the LabVIEW source that has the subsystems, and I'm going to open the VI that executes the SCPI command. So when the SCPI command handler says, oh, there's a recipe command that was sent down, this is the VI that will receive the call when a recipe command is run. And I'm going to apply a breakpoint here and then save it. And then I'm going to turn on wire probing. Okay, and this is kind of the confusing part where I basically jump back over to my Macintosh terminal, and I think I'm still connected. This is something that could go wrong. I type recipe run, and it didn't go wrong. So the Mac terminal has sent a TCP/IP command to run the recipe, and now on the embedded computer inside of my benchtop instrument, you'll see it hasn't started running the recipe yet. And, well, you guys can't see that anyway. I'm not going to run the picture-in-picture because you'll just see the screen change, and that's probably good enough. And so basically what's going to happen here is you can see it's parsing the command and it's executing the run frame of this case structure. And I've got some hard-coded stuff, so it always runs the same recipe. So my demo works, or is easier. So here it's going to call the run recipe function. And you can see now the screen changed and it's running. It still has not sent a response back here, so we haven't got the OK recipe run, because that happens once this gets called. And then now that was called, and now we see it says OK recipe run. So that's just kind of a quick demo of basically what happens is the LabVIEW code that executes that recipe run is a callback function that gets registered by the framework when it starts up. All right. And then what I'm going to do is I'm going to, so that's a clone. I'm going to remove my breakpoint so that any future demos work. Clear breakpoint. And this kind of model for development, I'll get into some of the details why it's nice, but one thing that's kind of cool too is during the development phase we can have source code control on this machine. So any changes that are made on this machine can be checked into source code control, and we can also plug in an external monitor so that we don't have to remote desktop for engineering panels, but operators can go through kind of a standard interface. I'll talk a little bit more about the value proposition there in a second. Okay. So now I've closed the remote desktop, and now I'm looking at my Mac again. And okay. Were there any questions? I've done a lot of talking so far. All right. Has anybody done anything like this? Built a SCPI server for their instruments? A few people, yeah. And I'll maybe ask some more questions. Hey, good segue, huh? The different API technologies, and we'll talk a little bit about it. So, SCPI is kind of legacy. It's nice. It's kind of easy, text-based, but the new LabVIEW jocks coming up through the ranks aren't really doing a whole lot of SCPI these days. Web services is where it's at, right? 2013. There's no you can build your own SCPI server for your apps now. You're building web services that use basically XML and JSON as the sort of the data formatting scheme. Other API technologies, you can write DLLs. We heard somebody talking about that, Fabiola. Give the C programmers something to do. Network shared variables, those provide an API over the network to do stuff. And they definitely serve a purpose. File I/O, that's old school. Dropbox, hey, now you've got network connectivity, and you guys might laugh, but some of these things like File I/O and Dropbox can be pretty okay solutions. Let somebody else kind of handle the network layer, security, user account management, and things like that. For one-off systems, maybe those are good options. So I wanted to sort of ask, what other types of technologies are people using, or what are the preferred technologies for building APIs to your systems? I guess I'll start out. Who's building APIs to their systems right now? Awesome. How many of you guys are doing that using web services, XML? Okay, there was a big kind of difference there. What are you guys using if you're not using web services? Yeah. Uh-huh. Okay. And what protocols over UDP? Is this a custom protocol that was implemented in-house? Yeah. Who else? Yeah, James, we can wait for the mic. Yeah. Yeah. Awesome. Who else? I'm curious. There's a big difference in the number of hands. What technologies, API technologies, are you using? Modbus, and yeah, so that's a protocol for communicating between a network of devices on that serial interface.
Traditionally, we've done ours with custom or PCIe, but a couple of my engineers are experimenting with Protobus, which is something Google created. I don't know much more about that other than standard.
Well, we should all Google that.
Yeah, I was just going to second the comment on that. We build classes for all of our classes and we sometimes augment those images by allowing them to talk over TCP/IP, custom TCP/IP, over large ranges that we have to classes.
Yeah, cool. One of the things that I think is pretty interesting is like this idea of, you know, objects being active objects, right? And they can live in your application, they can be local, you know, or they could be remote. It'd be nice in LabVIEW if there was an easy way to, you know, call a class, you know, by reference, but it's not on my machine here, it's over on another machine. There's a lot of work that's involved in developing the protocol, you know, the connectivity, the security, and then the language bindings. So having an API, for example, if it's a SCPI API for an instrument, you need to create language bindings, or in the case of LabVIEW, an instrument driver. And so one of the things that really, you know, helped LabVIEW was that National Instruments made a considerable investment in the instrument driver network, which now meant that if you had LabVIEW, you could talk to just about any boxed instrument. And so if you have a product that has an API, it often behooves you, unless you know you have thousands of API users that are going to go do it for you, to create the language bindings or the library LabVIEW toolkit for your device, you know, based on the language communities that you anticipate would be using it. We will often create language bindings for Python. I'm going to show you guys a quick demo of that. You know, .NET, you know, I could rattle off languages all day. What types of languages do you guys see people using and needing APIs for your systems other than the ones listed? Or maybe just emphasizing ones that are listed? MATLAB, okay. .NET, Others? SQL interfaces to instruments? So the database programmers can oh, okay. APIs to databases? Yeah, okay. Yeah? Oh, okay. And so what does command line interface mean? Because it's pretty interesting, because that's an aspect of something I've already shown, which is kind of the telnet interface. What types of things? A Windows batch file? Okay. Yeah. Yeah, one thing that's pretty interesting about the command line interface is that in some senses it's both a user interface, right? I could interactively type in my commands and get responses, but if you're in the interactive environment of a language or IDE, for example, Python, MATLAB, you know, whatever, maybe Linux shell, you can actually, you know, do some scripting. You can do looping, variable assignments, and things like that, and then you can put those in scripts and execute them. And I'll actually show a demo of that. First, I wanted to introduce another concept, which is the idea of external versus internal APIs. So external public APIs are callable from outside the system, generally by kind of any class of user. Whereas internal private APIs should really only be callable from, let's say, inside the system or a more tightly controlled environment. You know, people that you can, you know, call up and say, hey, I'm going to break your stuff because we changed the under the hood implementation. And now I'll segue. I wanted to talk a little bit about kind of like kind of why we've set up our prototyping system this way. In terms of kind of the business value it provides to our customers in this rapid development process. So basically, our customers, probably a lot like yours, they call you when they've got a big tangled mess of hardware in a lab bench, and they say, hey, we've our CTO has been working weeks on end to prototype the technology. The investors gave us $1 million. Now we need to build 5 of them and ship them to customers, and it has to fit in the box. And they say, and we don't have time to tell the C developers how our system works. We've got the LabVIEW code. We hear you can build executables in LabVIEW. Can you do that? And they say yes. They say great. Well, just do that. And once you finish that, we're gonna hire some real software people, and then they're gonna come in and rewrite everything in C. And then what ends up happening is we build the executable, and they say, we need to get this next phase done in a couple months, and we just need these features. Can you do that? And how much is it going to cost? And you say, yeah, we can do that, no problem. And they keep doing that, and then next thing you know, it looks like a real system. It looks like it has real software, but it only has LabVIEW on it, right? And then we're victims of our own success, right? So we help our customers basically reap that huge value proposition of staying on LabVIEW. Anytime you migrate, you bring in the Java team, the C team, nothing against those languages, but now you're teaching real software people how to do real engineering, right? Real systems development. And not that they can't pick that up, but it's oftentimes a different domain vocabulary. So what do? You write a detailed specification. You hand the specification to them. You hire a QA person, and they're going down the list, checking things off. You're adding huge overhead for, large volume production systems. There could be huge value opportunities there for reduction in cost of goods by doing a bunch of custom stuff with a real software team targeting, real embedded systems. But there's risk of migration, and there's cost, time, overhead in migration. And then once your engineers change their design, because they're going to want to change their design, then you have to rev the spec, pass it over the fence to the software team. You've got to do regression testing. So for low volume, high cost, high impact systems, staying on LabVIEW the whole way makes a lot of sense if you can do the software engineering work, do the professional software stuff. So one thing that happens when you create an API and you keep the system software, system control software in the box, and you push the lab code out of the box and force it to go through an API, is you actually now have a distinction between the two, and you can manage them separately. And so I like to think of system software as the stuff that controls the system, per the specification. Whereas lab code is used to generate data to evolve the specification. People are in the lab, acquire, analyze, present, automate, measure, verify. They're trying to get their mechanical design, their optics design, their chemistry, all this stuff down so that they can actually ship their product, and then they're changing the consumable, changing the motors, changing the camera, telling you, I want you to use this new camera instead of the old camera. You're then changing the system software to meet that new specification. So the system software is the core functionality of the product, where the lab code is really characterization and verification. The system software ships with the product, whereas lab code supports product R&D, and it might feed forward into the shipping product, if the experimental stuff turns out that it works. The way that you do that is really to treat the system software as essentially kind of a separate software product, separate package, and expose an API that allows lab code to call into it. So tying back into your systems that you're building, that's just another example of how APIs can really help with system development. What I wanted to show here too is a little bit about private APIs, and I don't have a great setup slide for this, but one of the things that we've done is we've exposed all of the different subsystems that are kind of dynamically loaded through a private API, and then we've created language bindings in Python, and then the LabVIEW code basically can call recipes that are Python-based recipes that call into the LabVIEW subsystems, and we're using Python as a text-based, essentially recipe language that basically allows the product development team, like the chemists, the process engineers, to actively participate in some of the highly sequential, non-real-time logic of the instrument. And so when we saw the progress bar going, what that was actually doing is it was calling a Python script. So I'm going to show you under the hood how that works a little bit. Hopefully you guys find that cool. So again, I'm in Parallels Desktop on my Mac, and then I'm going to remote desktop. Hopefully this happens reasonably quick. And if I go up into the Python source, so basically when we hit run recipe, what's being called is this Python script. And just to reiterate now, we're looking at the embedded computer running Windows 7 right now, and it's actually running a Python IDE, and we're seeing the script. And if we were to run it, it would be running inside here, calling into private APIs. So essentially what it does is, it imports some modules, a LabVIEW connectivity module. It opens a connection to LabVIEW, creates some objects, and then basically starts iterating through some process steps, and then it updates front panel stuff, it finishes up, and it disconnects. And what I wanted to show is, first of all, that recipe is a Python script, but I'm going to attempt to open this, and I'm going to import the module, and what I'm hoping is that then that allows me to interactively, through a command line interface, command prompt, interact with my instrument. So hopefully this won't go horribly wrong. All right. So let's see here. Do I have a LabVIEW? All right. I'm just going to rename it instrument equals LabVIEW, so that now when I call it, it's called instrument instead. So when I hit instrument dot, one cool thing about the Python IDE here is it's showing me essentially a list of the different sub objects or methods that can be called. And I'm going to call the connect method, and it's going to open a connection to the instrument. And now if I type this, you can see that it's got a much larger list of options, that it's populated with some of the subsystems, the logical subsystems in my application that were dynamically loaded by our framework. And what I'm going to do here is I'm just going to call this IO manager, and then I'm going to feed it the name of an IO tag, which is linked to a little red button on the instrument instance has no call method. So let's see. Oh yeah, you're right. So I'm not a real programmer anymore. Not even a real LabVIEW programmer. Well, this is Python, so I'll give myself a break. Manager dot aha, and this is a DI read, and then okay, and it works. So this is inverted logic. So 1 means don't shut down, and 0 means shut down. And if I push this button, you can see it pops open a window, and I can tell it to do stuff or not. So we have a NI USB data acquisition board in here that's basically monitoring this button that LabVIEW's monitoring. So I'm gonna copy and paste this here so that I can just hit return while I'm holding the button. So take my word for it, I'm holding the button, and now it shows a 0. And so that's just a quick example of how I can use Python to interactively communicate with the private interfaces of the instrument. And we find that, for example, like the mechanical engineers and things like that who maybe needs to do a burn-in test. Maybe it's not a power button, maybe it's a door sensor on the instrument. They'll basically write a script that opens and closes the sample tray overnight, and they're going to log the state of the door sensor or the sample tray sensor every time they do it, and they just want to do a burn-in characterization. Or an optics engineer wants to move the stage to a certain point and take a picture of their sample consumable, move to all these different spots, log the data. So they want to use the functionality of the system in an R&D mode, but they're not writing software that's going to ship on the instrument. They're doing R&D characterizations. Okay. So again, we couldn't do that without APIs. So while I think this is kind of cool doing Python and remote desktop connections and stuff like that, the point is it adds value to the customers during their R&D process. So hopefully, today I've made an impression on you guys that APIs are cool and that they add value to your systems and your customer systems. Yeah, David? Oh.
So back to the Python point.
Yeah.
Just because you haven't trained those engineers to make it for the lab.
Yeah. Well, so there's sort of two parts to that. So one part is the work that it takes me to give them a LabVIEW-based API, do the language bindings, when the interfaces change, update my LabVIEW toolkit so that they can do it. Of course, they could do it if I taught them LabVIEW, right? With Python, all of those language bindings actually are kind of like auto-discovered. They're very, it's kind of loosely typed. You have to know what the API is. And when they're kind of developing throwaway R&D code, personally, I'd love if it were easier to do it in LabVIEW. And the other aspect of it, though, is JKI has been brought into our customers to help them get their product shipping. They didn't bring us in there to teach LabVIEW to their mechanical engineer, their chemist, their optics person, their whoever. No, they know how to use a text editor. And they're smart, and they took an intro to programming class in college. And if I give the mechanical engineer a script that says import LabVIEW as instrument, connect, for X and 1,000, open the door, close the door, read the sensor, write the file, close the instrument, and hand them that script, they can go in and they can fiddle with it, and they don't really need to spend an hour a day in a course because it's pretty easy. It is free of cost, yeah, to them, and I don't necessarily want to turn this into a plug for Python, but the reasons I love Python are very similar to the reasons why I like LabVIEW. It's cross-platform. It's very interactive. Like I was typing, connect, call this function. It's the same way I'd open a blank VI and drop nodes and things like that. And it's really useful for the recipe portion of our code. We really only use it for highly sequential, very simple stuff. Anytime things become parallelized, real-time, complex, that stuff gets pulled into LabVIEW. Yeah, Justin?
What I would just add to that is, the whole, well, they could do it in LabVIEw written question, is really relevant, especially for people in this room. But what we found, and what eventually led us to do this on a lot of projects, is that in more than one case, being able to have somebody at the customer who really thinks they know Python and can operate a text editor comfortably, and being able to give them sort of the boundary layer there, where we can do everything we're good at doing in LabVIEW, they can talk to me in Python, ends up being the difference between success and failure for their project. And if it's between success and failure for their project, I don't care if we do LabVIEW. I want them to think that they are an awesome LabVIEW company to do this instrument, and then they have a Python interface. If that's what they're happy with, then cool. So that's how we sort of evolved to get to that point of doing projects. And we don't do that we don't force that down the throat anymore.
And in our sales cycle too, when a company says, hey, our CTIO wrote some LabVIEW code that automates the prototype, and we say we can put your code in the box, plug it into our system, you have a professional interface, we can theme it with your logo, and you can bring your investors in next week and show them your shippable product, and your engineers can basically write recipe scripts in Python in a text editor and automation their stuff. They go, okay, yeah, great. When can you start? And that's really an opportunity for us to engage with their engineers and teach them the value of LabVIEW. But they haven't paid us to come in and be LabVIEW instructors. Now, I would all the things that I love that we can do here, like I'd love to see in LabVIEW. I'd love to be able to very quickly create a system and to keep separate my system code from the interactive environment, to automate the process of taking the public and private APIs that my system has, and to be able to have APIs that the user can call from within their kind of lab code scripting environment. But right now those features don't exist. We don't have active objects and things like that. Yeah, Norm.
So I want to open up a question to yourself and then also to the audience as well, just with regards to API. For what you've done, you've created a program that runs on the embedded system, and then post facto, or probably kind of in the process, created an API to talk to that always running program. Mm-hmm. And that works, I mean, for the design pitch out there, it makes a lot of sense. But for some of us in the variety of systems that we end up using, some of the APIs that we make, say it's like for like a load cell. If we had to make an API for a load cell, very often we might create just the discrete calls to maybe talk to the serial port to get the information. And, or say it's to like a DMM inside PXI chassis or something of that nature. I'd be interesting to hear your thoughts on the process of trying to create more of a passive API that you're able to have a UI attached to the necessary things associated with that. It's related in terms of the API aspect of it, or to hear other people in terms of taking that paradigm instead of creating the app, creating the API for it, creating the API and then allowing a UI to kind of attach itself to that as well. Thus allowing to have, because if you do that the way that you got it right now, that app has got to be rock solid.
They're shipping it to customers, yeah.
Yes.
So I think based on the amount of time I have, maybe we'll explore that offline over a beer. I know there's a half-hour break coming up, and I have one more cool demo that I'll show you. So we at JKI, we think touch wireless mobile technologies are really cool. The touch screen on the instrument is one example. We're looking at other technologies, Windows 8 on the Surface, Qt, iPad stuff. What I wanted to show you guys here is this iPad app is connected to the instrument here, and unfortunately we touched the touchscreen display with the cable. Apparently it's not capacitive. And if I toggle this, we're going to get crazy here. I'm going to basically run this from my iPad. I'm going to zoom. So here's the iPad app. Data dashboard app. Well, see, the thing is our customers, when we're showing this cool stuff to, the people building the biotech instrument, they don't care about data dashboard. They want to show their investors, iPad apps, and then, when they get funded, they'll hire iPad app developers to do this stuff. So here we're going to run. Hold on, there we go. So I hit the run button, and what I'm hoping is the progress bar progresses, and hopefully on the screen that I can't see right now, you saw the progress bar. Cool. So that is pretty much it. Let's see here. All right, so thank you. I'm over time, so if there's questions, we can maybe do that later. One more thing, so we're just super excited about the type of stuff that we're doing, and so we've got big plans to really revolutionize the way that people build instruments. We think that the old way of doing things, hiring real software teams and real embedded teams, is just so boring and slow and expensive. And so we're looking to hire people that are really passionate about LabVIEW, want to work with a great team on really impactful stuff. For customers that are building stuff that changes the world, like next generation gene sequencers, green technologies, and stuff like that. So I think that is really the end. All right, thanks.